improving the verification predictability and efficiency using the big data. The big data is a term of data that has been around for many years. The list of applications for big data are endless, but the process stays the same: capture, process, analyze. And so what should this technology help improve your verification process efficiency and predict your next chip sign-off? By providing a big data infrastructure, the state-of-the-art technology within the verification environment, the combination of all verification metrics allows all resources to be used as efficiently as possible and enables the process of improving user predictive analysis. This paper will cover the technology, metrics, and process, and will explore a number of techniques enabled by such infrastructure. Instruction. Big data is a term that has been around for more than 20 years. It was initially defined as data sets, captures, and aimed at processed in a total period of time beyond the ability of normal software tools. The only constant in big data sizes over this time is that it's been a moving target driven by improvement in parallel processing, power, and cheaper storage capacity. Today, most of the industry uses 3V model to define the challenging and opportunity of the big data and three-dimensional: volume, velocity, variety. Lately, this has been expanded to a machine learning and digital footprint. The list of applications is endless. The process is the same: capture, process, analyze. Why should technology help your verification process efficiency and predict it to your next chip sign-off? Today's verification environment has been collaborative due to the size of the devices, geographically dispersed teams, and pressure on time to market. It requires the efficiency to use of every cycle, managing hardware and software and personnel resources. This paper will define the typical verification environment and the data is often leaves and captures across the period of time. It will show how the process of the capture, process, and analyze can be applied to the improve productivity and efficiency of the whole verification process. This requires a flexible infrastructure that allows data to be extracted from the multiple systems and make up the typical verification flow. There must be an essential laboratory that is able to store data in a common way, so that the data is managed to be kept and clean and relevant not only over the project duration, but also into the future to allow comparison and prediction on the other hand and new project. This paper will explore how new web-ready technology can be applied to the hardware development flow to provide a plug-and-play infrastructure for collaboration. It also highlights some of the types of the analysis and the insights that are possible by combining common coverage metrics with those normally lost data metric, as well as the interrelationship between those metrics. The ability to see and gather the metric over time can provide a great insight into process. Historical coverage data trend over time alone can give indication of how much more time is needed to complete sign-off. Being able to plot these single metrics of together the same graph also opens up information that is often lost. This paper will also show the examples other sites and can be gained by looking at the cross-analysis between the bit closure rate and the source code churn. And high, which then combined with the coverage metric can help predict progress toward sign-off. It will show how historical data can be used to spot similar patterns of the event, and how recording the little more of the metadata within the existing system allows the cross-analytic to figure out the information like how effective the new technology or tools has been based on a past project. It also allows the calculation of further metrics available from the data. such as the mean time between the bug fix and the mean time between the regression failures, the last time a test passed or failed, and the tool licensed by a specific users. Allowing us to answer the predictive questions, we'll have enough formal licenses for our peak usage of the next project. So what is big data? The definition of big data was always targeted toward sets of data so large the traditional processing software is inadequate to deal with them in an unusual amount of time. Not only was there amount of time the data, but also the diverse types of data of which is unclear at the point of collaboration, how they will be useful that they analyzed. Fundamentals include the storage of unstructured, semi-structured, and structured data. The main focus is normally on unstructured data. This tends to leave the opinion that we will understood a verification process with well understood data generation is not a big deal, is not a really big data. In 2001 research report and a related lecture, and a meta group, now Gartner, defined data growth, challenge, and opportunity as being three-dimensional. The three-dimensional were known as 3Vs: increasing volume, amount of data; velocity, speed of data movement; and variety, change of the data type and sources. This definition was later updated as it is not only the data but the technology and method used to be transformed into value that matter. The addition to the including machine learning to detect patterns and making predictions and the digital footprint, which is a cost-free byproduct by the digital interaction. The definition has changed, but there is no doubt of its impact of our daily life, the everyday life. Companies like Amazon and Facebook and Twitter and Google all make considerable revenue of the capturing and managing our data. For example, the Amazon captures and stores our digital footprint and processed data and then uses predictive analytics. Predictive analytics are part of the machine learning and is one of the major fundamentals that make a concept of the big data extremely interesting when applied to the verification process. Many industries have been transformed by big data analytics and machine learning. Many of these focuses on making larger revenue and using predictive analysis to predict such things as a big music kit and right genre for the that's the big TV show and or when to renew a phone contract. However, it is also being used to benefit the other aspects of our lives, like controlling energy generation by monitoring user habits and being kinder on the environment by predicting as peaks and throws. It is also being used by the healthcare where it is possible to use the mobile phone and social media usage to pinpoint the outbreak of diseases in Africa. It is also used in law and order where using the year of history and patterns of past crime data in inner cities. It is also able to predict the time and the location of the future crime and quite a minority report. Every one of these examples follow process capturing data under a central place and processing and management maintain the good housekeeping of the data and employing various methods of analysis, again, mainly involved predictive analysis. All of these concepts can be easily applied to the data with the verification environment. The typical verification environment. Verification is typically driven by the test plan document. The test plan is derived from the design specification and defined how to test or verify the design features. These features are typically tested by either a directed test or by some form of coverage combination of coverage that occurs that when a particular feature has been tested. Implementation is driven by the design specification and along with the stimulus in form of the test benches. It is typically kept in the source code management system, and a build and regression management system is also to use the various verification tools to first locate the areas of design that does not meet the specification, that is both, and second, to ensure that all functionality with the specification has been covered. Bugs active within the bug tracking system and cover closure is achieved by measuring the both code and function coverage and cross-referencing the test plan. All of the system and the stage mentioned above the produce data, and some of these sources are not typically gathered during the verification process. The process described above is also required both hardware in a way of the computer resources and licensed software, both of which we need to be efficiently. The computer resources typically controlled by a load sharing system, and the share license by the licensing system. Again, typical data from these resources is not gathered over the period of the verification process. The complete pictures of the typical process, the typical verification process, and the systems that produce data can be seen in Figure 1, the typical verification environment. There are many other metrics that could be gathered during the duration of the project if there were an infrastructure stored over the time, and some of which are covered in other papers. Some of these systems described above have the facility to store information over time and may be even analyze the data over time. But this allows the metric to seen in isolation. Which project the teams spread geographically? What is required in a system is a system that allows all of this data to save in a central repository that is visible in all locations. This allows collaborative authentication, access to be combined data, and ability to multiple projects to use the same resources. By gathering data across many projects over a period of time, the data value will improve just like any of a big data application talked about the last section. This will allow the predictive analysis techniques to be used in both project or across a project to be help the process. There are a number of statistics on general data growth. IBM stated in 2013 that 90% of the world data had been generated in last 2 years. Other newer reports stated that data is growing now up to 40% to 50% every year. Generally, with the verification process, space only a small fraction in a generated data during the project is saved, with some components saving more than others. However, without an infrastructure similar to one explained in the next section, too much of the data is detailed lost. Data can be a valuable tool organized in predicting is helping to drive future projects. 4. The new enabling technologies. One of the major requirements when the harvesting vast amounts of data is to have somewhere to store the data. With the verification process, some of the individual systems have a persistent store and repository, allowing a collaborative use model. For example, bug tracking and revision control. Others stores data for use in the that domain only, such as coverage or domain documents like a test plan and design specifications. Data management is a key requirement for this system, and there is a huge choice of the database infrastructure. Serve structured databases such as Microsoft SQL Server, Oracle, and the open source PostgreSQL and IBM DB2 contains mechanisms to ensure the reliability and consistency of the data and generated and are geared toward multi-user applications. These databases are designed to run on high-performance servers and carrying a correspondingly high level investment. The benefit achieved through the use of the server-based system, including flexibility, power, performance, and scalability. With the new need to manipulate large sets of complex data, some of which data are unstructured or semi-constructors. NoSQL databases have been more widespread. No SQL database is now structured on the common column load design on a traditional relational databases, but rather uses a more flexible data structure. The common model varies depending on the database. Some organize data by the key value pair, a graph or wide column. Common NoSQL database includes MongoDB, Cassandra, CouchDB, and HBase, and Redis. It's not possible to discuss big data technologies without mentioning Hadoop. Apache Hadoop describes an entire ecosystem of distributed computing tools centered on a file system, Hadoop Distributed File System, HDFS, and a resource negotiator. The core components are based on a paper authored by Google and were created by Yahoo. So the Hadoop run an application using the reduce algorithms where the data is processed by parallel different pieces nodes. Data is distributed and tracked as multi-copies stored over a cluster built for a community hardware, and the data stored on a server that go offline and dies can be automatically replicated from a known good copy. Enterprise database requires a heavy initial investment in resources, time, and money. This means that the genetic backend infrastructure must give the flexibility to choose the database technology, but still provide a security authentication and maintenance. Once the backend infrastructure is in place, the major investment involved building business logic to achieve the requirement another system views. The major blocks of the system can be viewed in Figure 2, technology stack block diagram. The front end is another major requirement for collaborative analysis and visualization of the data. Again, there are many new technology stacks giving map-ready visualization. HTML5 is often used to refer a range of the modern web technologies. Simply speaking, HTML is the language that web is written in. HTML5 is the most recent version of it. But because there are a lot of other technologies commonly used to create rich experiments in web, such as CSS3 and JavaScript, those get wrapped into abbreviation HTML5. There are many JavaScript libraries to choose from to implement to front-end client. This includes the Angular 2 and originally developed by Google, React, and originally developed by Facebook, and Bootstrap, originally developed by Twitter. It is also possible to run a library such as Node.js, which generates dynamic web page content on a web server side before sending it to the client. All of these libraries are extensively used in the web applications, have other library built upon them provide all kinds of visualization widgets, graph and tables, gauge, and more. As more complex more companies realize the benefit of implementing business intelligence software has been an increase in the number of vectors offering dashboard software. Dashboards provide a visual overview of organization data and analytics in an interactive dashboard that displays key performance metrics in various charts, graphs, and animations. This makes it possible to create a visualization of your application-specific data without needing them in most cases, so for software language still in the web technology. There are also many systems that are the web solutions to be developed using the scripting language the hardware designers are more familiar with, allowing more homegrown to be more easily developed. To such a system and Ruby on Rails or Python and Django. From technology standpoint, there is no clear winner between these two. They have a similarity both as a server-side framework, which has a community supplied set of extensions to help the building of the web application, and both are popular and trusted framework in the program world. This choice would probably come down to the preferred scripting language. One such a system developed for the purpose of metric gathering in the verification environment and using Ruby on Rails as details in 4 is beyond the scope of this paper that recommend which of the many technologies should be used to implement a big data system with the verification process. But commercially available tools would be needed to support multiple types of databases and be ready using the latest technology stacks. The 5. Single and cross-metric analysis. Once one of these systems is in place and to store data in a verification process, it's structurally required to input data from all the relevant sources. The system needs the ability to run an extractor either periodically or the one occurrence of a certain event. For example, samples of loading statistics of the computer resources need to be taken on a regular basis, at least every minute and maybe several times a minute, from a graded system or from the licensing system to monitoring which license features are currently in use. On the other hand, samples from a system like resources managed need to be taken every commit, and samples from a regression from a system must be taken every time it is run, which could be either periodically for nightly runs or event-driven for a commit for a smoke test. The instruction system needs to be flexible for achieve these requirements and must be adaptable to mine data from many resources. A table of resources examples of types of metrics can be extracted for a typical verification process is shown below. Table 1 extracted metric from the individual sources. Trending, or looking at a time series line graphs of a number of metrics details above can give a very good indication of how much time is needed to complete the sign-up time. The obvious metric code and functional coverage plotted over a period of time where the finish time is as close as 100% as possible. Bug closure and code churn are two other metrics that give a very good prediction of where you are in the verification process. The bugs closed over the period of the project will follow the standard S-curve, whereby earlier the process many bugs are closed in a short period of time until it slows for fewer bugs closed to a tour and of the bug process. This S-bugs relationship is allowed within the code churn rate, where the more code is touched and added in the early part of the project, while the toward the end of the code base stabilizes, starting these metrics across the project. This relationship can be used for within the high-level accuracy, which means that the sooner they are gathered, the sooner they can be used for future predictions. Insights are also possible by combining metrics with the same graph to help produce a more accurate pictures. This can be done by using current and past data by looking at metrics from different sources. The plotting both code and coverage functional coverage on the same time series scale tells us more about what is happening in the process. If the test code is a high but functional coverage is low, the coverage low and but functional coverage high, it means that either the functional coverage mode needs enhanced or that there are unused and unnecessary areas of design. Furthermore, if the coverage percentage are viewed along with the big count, it's possible to see a coverage number of data decreased because of addition to the coverage model. This is only possible when there is the infrastructure allowing more than just coverage percentage to be saved over the duration of the project. With all relevant metrics stored in the same place, the small functions can be built to allow the data be processed dynamically for generating up to minute views of the data, as well as the notification of when a certain event occurs. For example, visualization can be built to constantly monitor metrics such as the hardware and software resources usage. These visualizations include things like legal tables to show the current license feature being used by the individual or project team, or a gauge to show the current disk space usage or compute resource loading. By building rule-based notification system, the user could also set up the automatic monitor to show event on a news ticker, or send a manager to send an email to a particular person when a good or bad event happened. For example, the system can record a drop in a certain coverage metric or more than a particular amount of a particular period of time, or the fact that a lifetime or a particular bug has gone over a certain period of time. These smart functions should also be able to do housekeeping to keep the data clean and relevant. For example, downsampling techniques can be applied to a data window for a certain metric. Thus, when sampling the source metric at the rate of 1 to several times a minute, the data can be downsampled, keeping the trend and to reducing the storage needs. With such a data platform, domain-specific analysis is also possible, including deeper analysis that provides each host and the connected source data. This adds extra value and insight. For example, by adding an extra metadata to a source code, it is possible to calculate a functional, comment, and white space lines of code for either RT or HVL code. It is also possible to calculate the lines added, removed, or modified by each user. There are other mining techniques used in software development that can be used to learn how source files and up to changing together. This can be used to point to a cause of the potential problem. For example, analysis can tell that each time a particular source of file changes, there is a percentage chance to other files will change. If there is no region to particular files should change together, the analysis points to a part of the code worth investigating as a potential target for future refactoring. Adding extra metadata to a system, for example, adding the tools to use to find a particular bugs or an instance of the design where a bug is found, allow further analysis of the standard data. Calculating the time in each bug standing in progress for each verification method or a component makes it possible to show the mean time between fixes for each component for those methods, compare which is most effective. Mean time between the state changes in many of the metrics can be very useful to get more insight into process using both current values of trended values over time. This includes changes in test result, regression from pass to fail, or vice versa, and even changes in the state of the covered bin. Big data is not just about harvesting vast amounts of data, but more about the different relationships you can start to see when there's combined data. The insight derived from the data helps make better, faster decisions within the project across the project. This process can be improved by placing the cross references between metric domain. For example, by adding the ID reference has been fixed to a common commit into a source code revision system and recording the commit and the revision that a particular bug was found in and resolved into bug tracking system. This now allows not only cross analysis, and it is very simple to recreate a particular error scenario, but also allows deeper analysis into the relationship between the bugs and the code base and the method used to fix and locate the problem. The ability to look at these relationships is not only useful with the project, but the ability to analyze this data across the multiple projects opens up opportunity to learn more from the data would normally be lost. Other good examples of this include looking at the license history across the project, align patterns, usage, or picked uses to be compared to other metrics, such as increase in coverage. or the opening and closing of a box to be figured out where the when adding extra licenses would improve the productivity. The next section covers more in-depth analytic techniques. Data mining. The 6 is data mining and the predictive analysis. Maturing the data analytics is driving demand for automotive decision-making based on the reliable predictive analytics. Figure 3 is highlighted the maturing of the data and analytics, illustrating how we have moved to the descriptive and the diagnostics, the analytics to the predictive and the predescriptive analytics, resulting into the unleashing of the full potential of the data. Descriptive analysis by way of the report and the dashboard describe the dimension and the element measurement of the any aspect of the process, enabling users to report on goals and actual values of any metrics. Diagnostic analytics use more advanced and critical capabilities such as interactive visualization to enable the user to drill more easily into a data and discover new insight. Here the user is assuming it to be analytics is using the tools provided to mine data in the desired way. Predictive analytics is used after we become more mature, and diagnostic analysis and capability identify the root causes for any metric, data variance, as well as variables that can predict what measure to win in the future period. Some examples of the 43 analytic types of the have been given in this paper, but prescriptive analytics, which use insight from the predictive models, are integrated into processes to take correctiveness or optimizing actions. This section highlights some of the analytics that fall into a more accurate, more mature area of this graph. The debug cycle, where to do started, and two of the most time-consuming aspects within the verification process, with all coverage and assertion data in one place. It is possible to utilize data from the regression runs to suggest the starting points for debug. The basic principle is that all tests that cover a particular coverage point passed, the chances of that coverage point being the cause of an error is very low. If all tests that cover given a coverage point failed, and none of the tests that did not cover the same coverage point failed, the chances of a coverage point in question being the cause of the error is high. Taking tens of thousands of these coverage points in a typical design, it is possible to pinpoint likely causes of failures. This algorithm works along with the triaging process to pinpoint a single error as a starting point. The assumption is that we require significant numbers of the passing or failing tests. The test should not produce 100% coverage, and the coverage of various tests should have a minimal overlap with the coverage from the other tests. Essentially, what we want to calculate for each coverage point is the probability of a test result of a given test being a failure if the given the storage coverage point is covered by said test. The rating can be computed for the result of the given test being a failure if the given coverage point the rating can be computed for each coverage point, which tells us how much additional information about the overall pass or fail status of the test is contributed by each coverage point, and closely does the signature of a given coverage point match the test failure, pass or failure signature of the regression suit. The coverage point is the closest correlation to the pass or fail status signature is probably coverage point is closest at least one cause of the failures. This is an example of what is possible to data mining when the all information from the regression is gathered in one place. This approach has been patented in 5. The 7 is conclusion. The big data is not just harvesting vast amounts of data, but also align the explain of the differential the relationship you can start to see is by combining the data captured from the verification process. We've looked at the typical verification process and the systems that are used, which provide many useful metrics, some of which traditional often go uncaptured. Using some of the readily available technology, it is possible to start to gather various valuable data, which can help status and stays and more important to tomorrow's project. Data mined in the predictive analysis can be applied to data within the verification process, providing big data structure or platform with a state-of-the-art technology for verification environment allows a mixture of all verification metrics and can truly allow all resources to be used efficiently as possible, significantly improving the predictability of the entire process. Okay, thank you.